Good afternoon. My name is Camille Ginsburg, and I'm the Director of Accelerator Operations at Jefferson Lab. And today I'm going to talk to you about accelerators, smashing atoms for science. Catchy name. So what is an accelerator? A particle accelerator is a machine that uses electromagnetic fields to propel charged particles to high energies and also to contain them within a well-defined beam. And I'll tell you exactly how we do that at a high level. So why do we need accelerators? There are many different applications for accelerators. Perhaps the most important is medical applications, for example, cancer treatments, as well as isotope production for medical diagnostic tests. The semiconductor industry uses accelerators for ion beam implantation into semiconductors. They're used in manufacturing. They're used in dating archaeological samples. They're used in biological material and pharmaceutical research. A recent very interesting application was investigation of a COVID enzyme. You can see here a publication that was made based on data taken at the Argonne Advanced Photon Source in Illinois. But today, my focus is going to be on nuclear and particle physics research, and Jefferson Lab in particular. So if we were going to pick an accelerator for nuclear physics research, what particles should we accelerate? So protons and electrons are commonly used, but we can also use ion beams and heavy nuclei. In addition, protons can be used to make neutrons, and electrons can be used to make photons or a light beam, a beam of light. Particle beams can be smashed into stationary targets. Those are called fixed target experiments. Or beams can be smashed into each other, and those are called collider experiments. Electrons are point-like. They don't have any internal structure. And if you want very precise conditions, very precise measurements of your target, you might pick electrons. They're also commonly called precision machines. Protons, on the other hand, are composite particles containing quarks and gluons. And if you want a range of different particles to be created, and if you want highest energy, then you might pick protons. Those are often called discovery machines. And you can see our cartoon of two up quarks and a down quark with gluons, which is a proton cartoon, and then electron cartoon shows that the electron has no internal structure. So what shape should we choose for our accelerators? Well, magnetic fields are used to steer charged particles. Magnetic field has an opposite effect on opposite charges. Electric fields are used to accelerate charged particles or transfer energy to them. Like charges will repel and opposite charges will attract each other. There are two common shapes, circular accelerators, and in that case, particles gain energy each time they go around. But they have to be matched onto the same location each time they go around so that they get the same fields each time they go. And that can be tricky. But it does allow you to gain maximum acceleration in the smallest physical space. Charged particles do lose energy when they go in a curved path, and lower mass particles lose more energy than higher mass particles, and thus electrons lose more energy than protons. Linear accelerators in a straight line, particles will only pass through any portion a single time. So you don't have to worry about the matching so much, but it can be expensive to get to high energy because then you may have to have a very long line of acceleration. And that's because of high construction costs for a tunnel and also infrastructure costs. CEBAF is a bit of a hybrid, and I'll get to that a little later. Here are some examples of proton and electron accelerators. You may have heard of the Large Hadron Collider at CERN. There's a photograph shown here with the accelerator shown on top. It's actually underground, but it's a proton-proton collider, so the two beams collide. The maximum energy for particle creation is 7,000 giga-electron volts, or billion electron volts. I'll define an electron volt a little later, but you can use these numbers to compare the different accelerators. The circumference is about 17 miles, and among many interesting scientific discovery was the Higgs discovery a few years ago. Another example of proton collider is the Tevatron at Fermilab, which ran until 2011. The maximum energy in that case was 2,000 gigaelectron volts. Circumference is about 4 miles. And that machine was used for the top quark discovery. So these are higher energy machines and discovery machines. If you want to look at electron accelerators, there are a couple of examples here. The European XFEL, X-ray free electron laser, that's at the DAISY laboratory in Hamburg in Germany. The electron maximum energy is 17.5 TeV, and the length of the acceleration is about 2 miles. In this case, the electrons are used to create a photon beam, a beam of light that is very precise for probing materials, biological samples, and so on. The LCLS-2 linear accelerator, electron linear accelerator, is in Stanford, California. That has a maximum energy of 4 GeV, although it's going to have an upgrade soon. It has a length of almost 1 mile, and like the XFEL, it uses a precise photon beam to probe materials and so on. So let me go through a few accelerator concepts. No math here. Electron fields are used to accelerate charged particles. And here's an idealized example. On the left-hand side, there are two parallel plates, A and B. A has a negative charge, B has a positive charge. So the electron starts, by magic, we can put the electron close to plate A, and it's accelerated negative charge toward positive charge toward plate B. And at that time, it gains energy of 1 electron volt. So CEBAF maximum energy is 12 billion electron volts. So we need 12 billion of these to get 12 billion electron volts. Here's a little bit more realistic example. The blue shows a metal structure, which is used to set up electromagnetic fields. The electric field is shown by the red arrows. And the electrons approach each of these cells. And the way the fields are set up, each subsequent one has opposite direction. But at the time that the electrons reach the next cell, the field has switched. So it's an RF field that switches one way and then the other. So your electrons are always going to see an accelerating field. And here's an example, a photograph of an actual superconducting niobium accelerating cavity. It's not superconducting right now. It's not connected to anything cold. But you would have a beam of electrons coming from the left-hand side going all the way through. Your power comes in through a waveguide through this channel here, which sets up the electromagnetic fields in each of these cells that cause acceleration. So each of the two linear accelerators at CEBAF contains accelerating cavities similar to these. And to save operational costs, superconducting cavities are used for the acceleration at CEBAF. We have more than 400 similar cavities in total. Niobium cavities have to be cooled below 9 Kelvin to become superconducting. That's less than 400 degrees Fahrenheit. It's very, very cold, 9 degrees above absolute zero. When they are superconducting, niobium cavities have a very low surface resistance and generate very little heat. We use superfluid helium at 2 Kelvin, 2 degrees above absolute zero, to keep them cold and superconducting. So that's acceleration. Another concept is magnetic fields. Remember that magnets are used to steer beams, but they cannot transfer energy. So this is an example of a simple bar magnet. It has a north pole and a south pole, and the magnetic field lines are shown in black here with the direction going from north to south. The Earth itself is a dipole magnet. If you look at the Earth's magnetic field, you see it looks very similar to this example. And in fact, the magnetic field where I'm sitting right now at Jefferson Lab is about 1/2 of a Gauss, or a more precise number is given by NOAA. You can look it up online. CEBAF contains about 2,200 magnets, and the heaviest magnet is about 20,000 pounds, quite heavy. So I'm going to show a couple of examples of magnets similar to what we use. Dipole magnets are used to create a homogeneous magnetic field over some distance. particle that's injected into a dipole magnet travels on either a circular or a helical trajectory, meaning that's its path. The radius of motion of that circle or helix depends on the particle momentum. So they can be used for steering charged particle beams, or they can also be used for selecting particle momentum, for example, in a particle detector. And here's one example of what a dipole magnet might look like. These are coils that go around, and a particle beam would go through the middle of this. And then this is a cross section, not of this magnet, but of a dipole magnet. And you can see these are the coils. It's been sliced like this. And these are the coils, and you can see there are two poles, hence the name dipole. Quadrupole magnets are used for focusing or defocusing the charged particle beams. In a quadrupole magnet, the magnetic force in the center is 0, and then it gets higher as you move away from the center. The magnetic force toward the center would be toward the center in one plane and away from the center in another plane. And so we can use two quadrupoles or more with proper spacing, and then we can focus in both planes or defocus if we want to. So, and then here's an example, again, of the bar magnets put together to form a quadrupole, 1, 2, 3, 4 poles. And here's a slice of a real magnet, and again, 1, 2, 3, 4 poles. So let's move on to CEBAF. So at CEBAF, it's really an electron microscope for nuclear physics. It's dedicated to that. In our case, we have an incoming high-energy electron, which is hitting a target, and there's an outgoing scattered electron, and then there are outgoing other particles, depending on what the target is and other details about the experiment. And this, in this example, this is a proton. It's got 3 quarks, a lot of gluons, and then a couple of pairs that have arisen from the vacuum. So this is the CEBAF electron accelerator. An electron beam starts at the injector, shown here as the green cube. The electrons are very close to the speed of light almost immediately. They don't get any faster in the accelerator, they just gain energy. And so the electron beam can circulate up to 5.5 times around the track, like this. It can go up to 5.5 times. It can go up to 4 times to these 3 experimental halls. Sorry, up to 5 times in these, and 5.5 times to D. So what are shown here are the 2 linear accelerators. That's where the electrons gain energy. And these are the recirculation arcs, and it's full of magnets, which are used for steering. The lower energy circulations happen at the top, and the higher energies are at the bottom. To get superconducting cavities in our acceleration, we use a refrigeration plant shown by the blue cubes here, and I'll talk a little bit about each of those. So the key points are up to 5.5 rotations, but that's adjustable. We have 4 user facilities, and those are used all at the same time, or not, depending on the need. We can get up to 12 gigaelectron volts if we use 5.5 rotations. There's the injector, the 2 linear accelerators, the 2 recirculation arcs. The tunnel circumference is about 7/8 of a mile, and each of the superconducting linacs is about 1/4 of a mile long. And then practical aspects, the tunnel base that houses the accelerator is about 30 feet below the ground. The tunnel is 10 feet high and 13.5 feet wide. And the specific details of this accelerator make it so that experimenters come from all over the world because they want to use our unique facility. But let me talk about superconducting cryomodules. I talked about the superconducting cavities. Those cavities have to be near absolute 0 in a room that's at room temperature, or maybe even a little bit warmer. So the cavities are placed in a cryostat, which is also called a cryomodule, which is basically a large thermos containing the cryogenic distribution and thermal insulation that can keep the cavities cold. Typically, there are 8 cavities per cryomodule, and more than 50 cryomodules are present in CEBAF. The cryostats also include other equipment that I'm not going to talk about that is needed to power the cavities and to operate them. So this is an example of a cryo module. And again, this is about 10 feet, so a person might stand about that tall. So, and here is an example of a portion of the recirculation arcs also behind me. We're steering the beam with magnets here, and there's a different recirculation path depending on which time you're going around. Low energy is at the top, high energy is at the bottom. Cryogenics are really cool. All large particle accelerators use cryogenics to cool the superconducting accelerating cavities or high field magnets or both, usually with superfluid helium. Gaseous helium is delivered from trucks into large storage containers and then cooled to 4K and then vacuum pumped down to 2K to support CEBAF operation. You can see in this picture here, this is a gas delivery, and then here are some storage tanks that are used for the cryogenic system, and the scale is given by this car. JLab stores about 30,000 gallons of liquid helium on site. Helium specifically, when it goes from liquid to gas, it expands about 760 times. So that, if we were looking at helium gas, it would be enough to fill 10 million balloons. And that could lift about 85 tons or one fully grown fin whale. This is a picture of a fin whale, and we'd have to ask him if he wants to be lifted up by helium balloons. So operations doesn't happen by itself. The machine operates up to 34 weeks per year, and the shift crews contain one crew chief and two operators typically. Control room is staffed 24/7 with 3 crews per day, and we have component experts on call 24/7 in case there are any problems. The main challenges are keeping our experimenters happy and keeping the machine operating reliably, which go hand in hand. So here's a picture from our main control room. This is our crew chief, Mike. He has a special desk. There are 2 operators here, Dan and Brandy, and they're doing their work, and then there are 3 experts that have come in to help. So who works on accelerators? There are so many, this is not even all of them, but these are the ones that first came to mind as far as different roles. Accelerator operators and scientists may come naturally to your mind, but many kinds of technicians and engineers and computing people as well. And then as far as the demographics, we have a lot of veterans at the laboratory and many other demographic categories. So let me just introduce you to some kind of randomly selected people. Kiara is an operator. Ken is a crew chief, so that's a senior operator who's in charge of the crew at any particular time. Marcy, who's a scientist. Shirley, who's a cryogenic engineer. And then these teams are from our SRF Institute working on superconducting RF cavities research. And then Joe is doing some RF measurements here on this structure. It takes a lot of different people to make CEBAF go. So I'd like to acknowledge my colleagues Jay, Jonathan, and Paul who helped me with content for the talk. And then if you have some more information you'd like to study, I recommend these 3 sources, and I would just ask if anybody has any questions. Lauren?
Thank you, Camille. We have a few questions populated in the chat and a few pre-submitted, so we'll try to get through as many as possible in the remaining time. I would also encourage those attending to type in their questions now in the YouTube box chat. The first question we have is, how do the particles gain energy without gaining speed?
Okay, so this is relativity, and the thing is, one of the basic tenets of relativity, special relativity, is that nothing with mass can go faster than the speed of light. An electron is very, very light. It's not massive at all, and so it becomes close to the speed of light very quickly, but it still can gain energy. It could still be accelerated. I'm not sure if I answered your question. Yeah.
The next question we have is, do you ever have problems with earthquakes affecting CEBAF?
So not in my experience, but when I worked at Fermilab before, certainly there were earthquakes there. Any accelerator is going to be very sensitive to mechanical vibrations. If a truck drives over it, for example, a very massive truck, or if a subway is going nearby. I know accelerators can detect those kinds of mechanical vibrations, and it just really depends how large the mechanical vibration is, whether it really impacts your beam operation or not.
Okay, thank you. The next question is, how often do you run experiments in CEBAF?
So we can run experiments up to 34 weeks per year, but it depends on the particular year and whether we have upgrades going on or something like that. But I'll say up to 34 weeks per year.
Okay, and are there any other accelerators in the world like the CEBAF accelerator, and what makes it unique?
Okay, so CEBAF is the best accelerator, but there are certainly similarities to other accelerators. CEBAF was the first major accelerator to use superconducting RF technology and the first to use so-called CW operation, which means not pulsed, and that's probably too much of a concept for this presentation. But those two aspects were really unique when the machine first started, and it's still the most powerful CW, superconducting RF machine. But there are certainly similarities. The European XFEL uses similar superconducting RF cavities. The LCLS-2 accelerator at Stanford uses similar cavities and a similar technology as well. There are a few in the world. But yes, CEBAF is unique as far as its ability to investigate nuclear physics challenges.
Okay, great. Now, this is an interesting question. How does CEBAF compare with the electron accelerators in old televisions?
I think an electron in an old television would be most similar to the parallel plate example that I gave. It would be very, very simple and much lower energy. And of course, we put our electrons on a target instead of on a screen that would light up.
Okay. And can you tell us how much more massive do electrons get when you accelerate them?
That would require a calculation. I have not done that calculation. Yeah. Sorry.
Okay. The next question is, have you ever done anything with CEBAF other than nuclear physics research?
Sure. There are plenty of accelerator physics experiments that go on. We're investigating many different things. For example, using positrons instead of electrons. We have some experiments to consider whether we would like to increase the energy of the machine for new kinds of nuclear physics experiments. We do experiments to investigate different kinds of diagnostic equipment or new kinds of superconducting RF cavities. We look at, so sometimes some dirt can get into the SRF machine, and that's bad. It makes them not work very well. And so we want to understand if a tiny amount of dirt comes in, where does it come from? Does it travel around? So this kind of an experiment. So a lot of different experiments, whether they're to do with improvements to our nuclear physics capability, improvements to the accelerator operation, or just understanding better how the accelerator works.
Okay, great. This is probably the second to last question. We know that we just upgraded CEBAF with the 12 GeV upgrade. The question is, do you believe that we will have to upgrade CEBAF again, and why?
So we should have CEBAF running for decades into the future. There's a lot of interest from the nuclear physics community to do more experiments. And so we don't have a planned upgrade right now that would significantly impact the parameters of CEBAF, but we certainly could, and some folks are investigating, for example, whether we would want to run at significantly higher energy, like doubling the energy. But we are doing upgrades all the time. For example, we're just finishing an upgrade in which we replaced some major portion of our cryogenic system. And that, I mean, that's a lot of money and a lot of effort by people that will go into improving the CEBAF reliability. And many upgrades of different components. We have a new cryomodule type with a new type of cavity, similar to what I showed, but still new. So we have continual upgrades all the time, but a major upgrade, we don't have specific plans right now.
Okay. Another question. This participant believes that photons are released when the E-beam is steered through the arcs. Anything done with these photons?
Try to get them not to irradiate stuff. That's absolutely correct. Any charged particle that goes in an arc is going to release photons. But there are, and in fact, there's a whole branch of physics that uses those photons, but at CEBAF we do not use them. They are a nuisance for us. They can cause problems in the machine, like vacuum leaks and so on. We don't use them for science.
Okay, and this will probably be the last question. What was your favorite experiment?
Do you want to also ask me which is my favorite child? Lauren, I don't think I can answer that question. I'm sorry. I love all of my experiments.
Good answer, Camille. Okay, I think that's probably all the time that we have for questions. I'll give it back to you to wrap us up. Thank you.
Okay. So I want to thank you all for joining us today and announce that we have as our next Bite-Size Science presentation, AI in a Nutshell by David Lawrence, and that will be on July 8th. So please join us for that, and thanks again for joining us.